There are discoveries that make science feel larger, and then there are discoveries that make certainty feel smaller. Most of the time, astronomy advances in a way that is almost gentle. A sharper image arrives, a better spectrum refines an old estimate, a simulation improves. A theory bends a little, then settles again. The universe reveals itself by degrees, and our understanding grows not through shocks, but through patience. But every so often, light arrives from so far away, from so early, from so deep inside cosmic history, that it does more than add a detail. It changes the emotional temperature of the whole subject. It reminds us that knowledge is not a monument, it is scaffolding. Useful, elegant, often impressive scaffolding, but scaffolding all the same. Because somewhere in the darkness, beyond the most distant stars our ancestors ever imagined, astronomers have found objects that seem to have matured too quickly. Galaxies that look too bright too early. Galaxies that seem too massive too early. Galaxies with oxygen and heavy elements where there should barely have been time to make them. Galaxies whose light appears to escape through a universe that should still have been shrouded in neutral hydrogen. And even a galaxy that seems to have settled into orderly rotation long before cosmic history was supposed to allow that kind of grace. In headlines, these objects are described with a phrase designed to arrest the mind. They shouldn't exist. That phrase is dramatic. It is also incomplete. The universe has not violated logic. Space has not produced a contradiction. No physical law has stood up in protest. What has happened is subtler, and for science, far more unsettling. Nature has drifted away from expectation. Observations have begun pressing against the timelines, efficiencies, and developmental stories that astronomers thought they understood about the first few 100 million years after the Big Bang. And that matters because the early universe is not just another chapter in cosmic history. It is the chapter where everything else becomes possible. When we look into deep space, we are not just looking far away. We are looking back toward origin. We are watching the universe in youth. We are seeing the first galaxies emerge from darkness, the first stars transform simple gas into complex matter, the first bubbles of transparency open in a fog-filled cosmos. The deeper we look, the closer we get to the era when the universe was still deciding what kind of place it would become. That is why these discoveries feel so charged. If a strange object appears in the modern universe, we can always blame age. Give reality billions of years and it has time to do almost anything. But if something startling appears near the beginning, age cannot rescue us. There has not been enough time for slow accidents, leisurely evolution, or endless cosmic rehearsal. The universe is forced to move quickly, and if it moves faster than our models expect, then our models have to answer for it. Tonight, we are going to follow this story from the ground up. We will ask what deep space really means. We will trace how telescopes can turn ancient light into history. We will walk into cosmic dawn, into the long darkness after the Big Bang, into the era when the first stars ignited and the first galaxies formed. We will examine the discoveries that triggered this new wave of astonishment, surprisingly mature early galaxies, oxygen-rich systems like JADES-GS-Z, 14-0, unexpectedly strong Lyman-alpha emission from JADES-GS-Z, 13-1, and the orderly rotating disk galaxy known as Rebels 25. We will ask why scientists expected something different. We will ask what "shouldn't exist" actually means in the language of real science. We will ask what possible explanations are now on the table, from revised stellar physics to unusual black hole growth to the simple but uncomfortable possibility that the early universe was better at building structure than we gave it credit for. And we will ask an even larger question beneath all of it. What does it mean if the universe learned how to grow up faster than we thought? Because sometimes the deepest scientific mystery is not that reality is impossible. It is that reality is more capable than theory expected. The phrase deep space sounds geographical. It suggests remoteness, emptiness, a far-off region detached from the world of ordinary experience. But in astronomy, distance is never just distance. Distance is delay. Distance is memory. Distance is time made visible. Light travels fast, but not infinitely fast. That single fact gives astronomy its strange power. When you look at the moon, you do not see it as it is in this instant. You see it as it was a little over a second ago. The sun arrives 8 minutes late. The nearest star beyond the sun arrives years late. Galaxies arrive millions of years late. The deepest galaxies we can detect arrive from a time so ancient that their light began its journey before Earth existed, before the sun formed, before the Milky Way finished becoming itself. A telescope is not only an instrument for seeing distant things, it is an instrument for seeing delayed things. This means astronomy is unlike almost any other science. In most fields, the more powerful your tools become, the more closely you approach the present state of the system. In cosmology, more power does the opposite. Better instruments do not just sharpen the current universe, they tunnel backward into older versions of it. That is what makes deep space so philosophically strange. A sufficiently distant image is not a portrait of what is out there now. It is a recovered scene from a universe that no longer exists in that form. The further away we look, the younger the cosmos becomes. A deep field image is not simply crowded with objects, it is layered with eras. This is also what gives the latest discoveries their force. Scientists are not merely finding unusual galaxies somewhere out in the dark. They are finding them near the beginning of cosmic structure, in an age when the universe should still have been comparatively simple. These are not systems with 10 billion years of mergers, star formation, recycling, and chance behind them. They belong to a time when reality was still close to its opening conditions. And opening conditions matter. When physicists and astronomers build models of the universe, the early chapters are often where the cleanest expectations live. The further forward you move in time, the messier everything becomes. Local environments diverge, histories accumulate, small differences amplify. But near the beginning, theory expects a more disciplined relationship between what should happen and what actually can happen. So when deep space starts returning surprises, those surprises are hard to ignore. Imagine reading a biography and discovering that, in the first pages, the subject has already done things that were supposed to require decades of development. You would not simply be surprised by the accomplishments, you would question the timeline. You would wonder whether your understanding of the subject by TM's growth had been too slow, too neat, too domesticated. That is what astronomers are now confronting. Some of the earliest observed galaxies seem too bright, too chemically mature, too dynamically organized, too visible through their environment. It is as though the universe in youth was moving with greater urgency than our comfortable models allowed. There is also a psychological reason these discoveries hit so hard. Human intuition is badly tuned for cosmological scales. We already struggle to feel the difference between 1,000,000 years and 1,000,000,000 years. We use language like early and late as if cosmic history were a human afternoon. But in the first few 100,000,000 years of the universe, timing is everything. Shifting a process forward by even a small fraction of 1,000,000,000 years can radically change what is possible. Add stars too early, and chemistry advances faster. Allow gas to cool more efficiently, and galaxies become brighter sooner. Let black holes grow rapidly, and surrounding space changes character. Near the beginning, small accelerations have enormous consequences. So when scientists say an object appears too mature too early, they are not being poetic. They are making a serious statement about developmental compression. They are saying that the universe seems to have squeezed too much history into too little time. And time, in cosmology, is not only chronology, it is budget. A young galaxy has a limited budget for everything it wants to become. A budget for collecting gas, a budget for forming stars, a budget for generating heavy elements, a budget for clearing local fog, a budget for settling into rotation. When an observed system appears to have overspent on several of those categories at once, astronomers take notice. To understand why that possibility matters, we need to understand how astronomers measure antiquity in the first place. Because these claims do not come from impressionistic awe, They come from redshift, spectroscopy, infrared sensitivity, and the careful translation of faint light into cosmic history. The discoveries may feel almost mythic, but the methods behind them are profoundly technical. And the mystery only becomes more powerful once we understand exactly how the evidence is built. There is a common misunderstanding about telescopes. People often think they work by making things look larger. That is true in a basic sense, but for modern astronomy, especially cosmology, magnification is almost the least interesting part of the story. The real magic lies in collection, separation, and interpretation. A great telescope gathers faint light. It disentangles that light into wavelengths, and from those wavelengths, it reconstructs conditions from ages no human being can ever visit. The James Webb Space Telescope was built for precisely this kind of reconstruction. Hubble changed how humanity sees the visible universe. Webb was designed to chase something even more elusive, the redshifted light of the earliest galaxies. As the universe expands, light traveling through space is stretched with it. Waves lengthen. Radiation emitted long ago at ultraviolet or visible wavelengths arrives to us, shifted into the infrared. The deeper into cosmic history an object lies, the more its light is displaced from the range human eyes can see. That is why looking far enough into the past requires more than a sharper camera. It requires a different kind of eye. Webb is that eye. Its enormous segmented mirror collects faint infrared light from the most distant known galaxies. Its sunshield protects the observatory from heat, allowing its instruments to remain cold and sensitive. Its detectors can not only image distant objects, but also spread their light into spectra, revealing the fingerprints of elements, redshift, gas conditions, and sometimes the broader physical story of a source. This is how astronomers identify very early galaxies. They do not simply point at a red smudge and declare that it must be ancient. They look for telltale breaks in the spectrum. They search for emission lines. They model how light has been shifted. They compare photometric estimates with spectroscopic confirmation. They test whether an object is truly distant or merely masquerading as distant through dust, unusual emission, or observational ambiguity. This matters because frontier astronomy is always vulnerable to illusion. A faint source can appear red because it is very distant, but also because dust has reddened it. A candidate galaxy can look brighter than expected because strong emission lines boost certain filters. Several nearby objects can blur into one. Active black holes can contaminate what looks like stellar light. Even the relationship between brightness and mass depends on assumptions about the stars producing that light. So when astronomers say they have found an object in deep space that challenges expectations, they are not making a casual claim. They are working through a hierarchy of evidence, caution, confirmation, and reinterpretation. That hierarchy has a history. Long before Webb, astronomers learned that the universe is full of false first impressions. The early 20th century taught them that spiral nebulae were not gas clouds inside the Milky Way, but galaxies far beyond it. Later decades taught them that a source R-Purs TM's color can conceal as much as it reveals, that dust can perform astrophysical mischief, that spectroscopic certainty is often harder and more valuable than photometric excitement. Astronomy has become a patient science precisely because the sky can imitate almost anything if you look too quickly. Webb operates in that tradition of disciplined suspicion. Its great achievement is not just that it sees farther. It sees farther with tools capable of interrogating what distance really means. When its instruments spread light into spectra, astronomers can look for specific discontinuities and features associated with hydrogen absorption, ionized gas, or chemical composition. Those details are what turn an image into a timeline. A picture alone can start a rumor. A spectrum can begin an argument. And yet, despite all of that caution, Webb has returned results that repeatedly tug in the same troubling direction. The early universe appears, in some cases, unexpectedly mature. Before Webb, astronomers had models for how the first galaxies should emerge. Those models were not fantasies. They were built from decades of theory, simulations, and the best prior observations available. Small dark matter halos form first. Gas falls in, stars ignite, heavy elements slowly accumulate through stellar life and death. Ultraviolet light struggles through a still neutral intergalactic medium. Early galaxies should therefore often be compact, messy, chemically primitive, and comparatively modest in scale. Webb has certainly found galaxies that fit parts of that picture, but it has also found enough that do not fit comfortably, that the field can no longer treat the discrepancy as background noise. This is the crucial point. The discoveries are not exciting because astronomers found one spectacular oddity. They are exciting because improved observation has started putting the old assumptions under pressure. The early universe is no longer a region where theory can speak largely unchallenged. It has become a place where nature answers back. And those answers are coming in several forms. Some galaxies appear too massive too early. Some seem too bright too early. Some seem chemically evolved too early. Some seem capable of clearing their surroundings too early. And some look structurally organized too early. Each of those surprises by itself might have been manageable. Together, they suggest that cosmic dawn may have unfolded with more speed, more efficiency, and more local complexity than the older picture emphasized. But to see why that is such a profound possibility, we need to step further back into the long darkness that came before stars. Because the first galaxies did not emerge into an already transparent, fully developed cosmos. They emerged into a universe still trying to become visible. Chapter 3. Before the first galaxies, the universe had to survive its own darkness. The universe did not begin with stars. It did not begin with galaxies, planets, chemistry, structure, or anything that would feel familiar to the modern sky. It began hot, dense, radiant, and nearly beyond ordinary description. In its earliest stages, matter and radiation were entangled in an environment too energetic for stable atoms to exist. The young cosmos was not empty, but it was not yet arranged into the things we now recognize as objects. Then, expansion began to cool it. As the universe stretched, conditions changed. Protons and electrons eventually combined to form neutral atoms, mostly hydrogen, with a substantial amount of helium. Light that had once been trapped in a hot plasma could now travel more freely. That ancient radiation still survives today as the cosmic microwave background, a relic glow from a universe only hundreds of thousands of years old. But after that release came a long, quiet interval. There were no stars yet, no galaxies in the modern sense. Matter existed, gravity was already at work, and tiny primordial fluctuations were beginning to deepen into structure, but the cosmos had not yet lit its great furnaces. This period is often called the cosmic dark ages. That phrase is poetic, but it is not just metaphor. The universe truly lacked concentrated luminous sources. There was no starlight in the way we understand it now. There were no galactic cities of flame. There was only gas, gravity, and time. Then, the first stars ignited. Exactly what those stars were like remains one of the most important open questions in cosmology. Because they formed from almost pristine gas with scarcely any heavy elements, they may have been very different from the stars common today. They were likely hotter, more massive on average, and far shorter lived. If so, they would have flooded their environments with intense ultraviolet radiation and then died violently, enriching their surroundings with the first heavy elements. These first stars did not merely illuminate the darkness, they transformed it. Their radiation ionized nearby hydrogen. Their death seeded gas clouds with new chemistry. Their existence enabled later generations of stars to form under different conditions. In time, stars gathered into the first galaxies, and the first galaxies began to reshape the intergalactic medium itself. This is where one of the great transitions in cosmic history enters the story. Ionization. After neutral hydrogen had filled the cosmos, ultraviolet radiation from early luminous sources began stripping electrons from that hydrogen, turning neutral atoms back into ionized plasma. But this did not happen everywhere at once. It happened in bubbles. Local clearings formed around the earliest radiation sources. Over time, those bubbles expanded, merged, and transformed the universe from a fog-laden environment into one increasingly transparent to light. This process matters profoundly for understanding deep space discoveries. A galaxy at very high redshift is not seen in isolation. Its light must travel through a surrounding environment whose opacity depends on how far reionization has progressed. That means early observations are shaped not just by what the galaxy intrinsically is, but by where it exists in the broader patchwork of cosmic dawn. So when astronomers expected early galaxies to look small, young, and chemically primitive, they were not simply making aesthetic assumptions. They were grounding those expectations in a universe still in transition. Gas had not had much time to collapse. Stars had not had much time to forge heavy elements. The intergalactic medium had not had much time to become transparent. Structure formation had begun, but it should still have been youthful, turbulent, and incomplete. That is why the new observations feel almost like time compression. If galaxies at these early epochs are already bright, enriched, and locally influential, then the engines of transformation must have spun up with remarkable speed. The first stars must have formed and died quickly. Ionized bubbles must have opened rapidly. Gas must have collapsed efficiently. In some cases, order itself must have emerged out of chaos on a schedule that many simulations treated as unlikely. The important thing to understand is that cosmic dawn was never expected to be simple, but it was expected to be slow enough to read. Now the possibility is emerging that it may have been faster than our reading scheme allowed, and when the first chapters of the universe begin to look rushed, every later chapter inherits the consequences. Because all of cosmic history rests on what happened here. If the first luminous sources were more powerful, then reionization may have advanced in a different pattern. If the earliest star formation was more extreme, then the timetable of chemical enrichment shifts. If black holes were active early, then even the first galaxies may have had central engines altering their growth. The modern universe is downstream of whatever happened in these first turbulent scenes. This is what gives deep space cosmology its emotional weight. We are not merely staring at old objects because old objects are interesting. We are tracing the first decisions the universe made about light, structure, chemistry, and visibility. We are trying to understand how a cosmos containing almost nothing familiar transformed itself into a cosmos where familiarity would one day be possible. That transformation had to begin somewhere, and what Webb is suggesting is that it may have begun not timidly but ferociously. Every great scientific instrument carries a promise before it carries a result. The promise of Galileo's telescope was that the heavens might not be perfect. The promise of radio astronomy was that the sky might be alive in wavelengths invisible to human sight. The promise of Hubble was that the universe, once seen clearly, would be grander and stranger than anyone comfortable with fuzzy pictures expected. The promise of Webb was more specific and more dangerous. Webb promised to look directly into the era that had previously been dominated by extrapolation. That is why its early discoveries felt like a release of pressure. For decades, astronomers had built careful pictures of cosmic dawn using the standard cosmological model, early observations, and increasingly sophisticated simulations. But there remained a region of history where theory still enjoyed a comparative advantage over data. The first few 100 million years after the Big Bang were partly understood and partly imagined. Webb was built to reduce the imagined part. When its deep images and spectra began to arrive, they did not reveal chaos in the ordinary sense. They revealed something more destabilizing. They revealed competence. Not human competence, of course. Cosmic competence. Galaxies that seemed unnervingly good at becoming substantial. Systems that looked as though they had advanced further along their developmental pathway than the calendar should have permitted. Some early candidates seemed startlingly bright. Some appeared surprisingly large in inferred stellar mass. Some looked redder than expected. And in astronomy, redness at extreme distances is a treacherous thing. It can mean old stars. It can mean dust. It can mean emission lines. It can mean the stretching of light by the expanding universe. It can also mean some combination of all of these. But in the first wave of Webb interpretation, enough objects appeared so luminous and so evolved-looking that astronomers began asking an uncomfortable question. Had the early universe built galaxies much faster than the models had been allowing? The public version of that question became simpler and more explosive. Webb had found galaxies that should not exist. The phrase spread because it compressed the emotional truth of the moment, even if it oversimplified the technical one. Something in the first deep views of the young universe was wrong, not necessarily with nature, but with expectation. This is where science becomes interesting in a specifically human way. When reality surprises us, our first temptation is usually to sort the surprise into one of two boxes. Either the discovery is a misunderstanding, and calmer analysis will make it ordinary, or it is a revolution, and everything we thought we knew is collapsing. Real scientific life usually happens between those boxes. The discovery is partly real, partly overinterpreted, partly resistant, partly unstable, and full of implications that only become legible with time. That is exactly what happened with Webb's early galaxy shock. Some of the most dramatic claims softened as better modeling and follow-up spectroscopy arrived. Distances changed, masses were revised, certain objects became less outrageous than first reported. But an important point is often missed here. A softened anomaly is not the same thing as a solved anomaly. Even after revision, enough tension remained that the early universe still looked more productive, more luminous, and more mature than the pre-Webb story had comfortably anticipated. This is the pattern we need to hold on to. The discoveries did not need to remain maximally sensational to remain scientifically disruptive. In fact, that is often how serious science works. A first claim arrives with a halo of astonishment. Then the halo contracts. Measurements sharpen, extremes become merely severe. But what survives that contraction is usually the real story. And the real story here is that Webb did not just find one strange object. It found a new regime of accountability. It forced the first galaxies to stop being a mostly theoretical chapter and start being an observational one. That change alone is historic. It means that simulations of early star formation, dark matter halos, feedback, and rionization are now being challenged by actual objects rather than elegant expectations. It means the cosmos, in one of its oldest accessible ages, now gets a vote. And the vote so far has been provocative. The young universe, at least in some places, may have been brighter, faster, and more structurally ambitious than our calmer stories allowed. The first wave of surprise prepared astronomers for a difficult decade. Then, particular objects began sharpening the problem into something even more specific. Brightness could be debated. Mass estimates could be revised. But chemistry, once it entered the conversation, made the puzzle harder to wave away. To understand why oxygen in an early galaxy matters so much, you have to think of chemistry as chronology. In ordinary life, a clock measures seconds, minutes, hours. In cosmology, certain elements measure process. They tell us what kinds of stars have existed, how many generations have lived and died, and how much recycling a galaxy has already undergone. Heavy elements are not merely substances. They are milestones. Hydrogen and helium are the primordial language of the universe. They emerged in abundance from the early cosmos. Nearly everything heavier was written later by stars: carbon, oxygen, neon, silicon, iron. These elements were forged in stellar interiors and in stellar explosions. In that sense, every chemically enriched galaxy is a record of previous stellar labor. That is why oxygen is so revealing. Massive stars can make oxygen quickly compared with the lifetimes of smaller stars. They live fast, burn hot, and die young. So in principle, oxygen can appear relatively early if massive star formation is efficient. But relatively early ESO is not the same as ESIS almost immediately. Detectable enrichment still requires the whole chain of formation, burning, death, and dispersal to begin and proceed with remarkable speed. JADES-GS-Z14-0 appears to suggest exactly that. This moves the problem from simple existence to developmental pace. The galaxy is not strange only because it is there. It is strange because it seems to have already been through enough stellar history to leave a chemical footprint. And that matters because it places pressure on multiple parts of theory at once. If the galaxy formed many massive stars early, then star formation in at least some young systems was extraordinarily efficient. If those stars enriched their environment rapidly, then mixing and recycling in the early universe may have been faster than many models emphasized. If chemical maturity and brightness coincide, then the same underlying stellar population might be responsible for both. And if such galaxies are not extremely rare, then the whole timeline of early cosmic development may need a more aggressive tempo. This is where the emotional meaning of the discovery deepens. We often imagine the young universe as simple because it was young. That intuition feels obvious, but astronomy repeatedly teaches us that simplicity of ingredients does not guarantee simplicity of outcomes. Hydrogen and helium under gravity are enough to begin building astonishing complexity. Add radiation, collapse, turbulence, shocks, and dark matter halos, and the result can be far richer, far sooner than human intuition finds comfortable. In that sense, oxygen in JADES-GS-Z14-0 is not just a chemical finding, it is a rebuke to slowness. It tells us that the universe may have been evolving on a faster internal schedule than our story permitted. Not everywhere, perhaps, not uniformly. But somewhere, under some conditions, cosmic history seems to have accelerated. And there's another subtle consequence. Heavy elements change future star formation. Metal-enriched gas cools differently from pristine gas. That means once a galaxy begins enriching itself, it also begins altering the kinds of stars and structures it can form next. Early enrichment is therefore not just evidence of a fast past, it is a lever on the future. A galaxy that matures chemically early can diverge rapidly from one that remains pristine. So chemical maturity in the deep universe does more than revise a timestamp. It changes the branching structure of cosmic evolution. A quickly enriched galaxy is not just ahead of schedule. It may enter a different developmental pathway altogether. This is why one oxygen-rich early galaxy matters even if it is rare. Rare objects define the frontier of possibility. They tell us what the universe can do, not merely what it usually does. And once possibility expands, theory has to either explain it as an exceptional but natural tale of the distribution, or admit that some of its assumptions were too restrictive. Either outcome is valuable. There's also a methodological lesson here. In frontier science, one of the most powerful kinds of evidence is evidence that ties separate puzzles together. Oxygen speaks not only to chemistry, but to star formation history. It speaks to the likely presence of massive short-lived stars. It speaks to how quickly light and death could reshape a galaxy. If the same kinds of stars also help explain unusual brightness and early ionizing power, then the anomaly begins to unify. It stops being a random collection of weird observations and starts becoming the shadow of a deeper mechanism. That is why oxygen changes more than the timeline. It changes the interpretive landscape. It forces astronomers to think less in terms of one-off surprises and more in terms of an altered ecosystem of cosmic dawn. Maybe the first galaxies were not isolated little star factories flickering into existence one by one. Maybe some of them were intense zones of rapid transformation, turning gas into radiation and chemistry with startling efficiency. But chemistry is only one part of the story, because galaxies do not simply carry signatures of their own evolution. Their light also carries signatures of the environment around them. And in another astonishing case, astronomers found an early galaxy whose light seemed to be passing through a cosmos that should still have been much harder to see through at all. There are few phrases in astronomy more beautiful and more frustrating than Lyman-alpha emission. Beautiful because it comes from hydrogen, the most abundant element in the universe, and because it offers one of the most sensitive probes of star formation and gas physics in distant galaxies. Frustrating, because the early universe makes that light incredibly hard to see. Lyman-alpha photons interact strongly with neutral hydrogen. During the era when ionization was incomplete, space between galaxies contained vast amounts of neutral hydrogen, which meant this kind of light could be scattered, absorbed, and effectively trapped. In simple terms, the early cosmos was foggy to Lyman-alpha. Even if galaxies produced it, the surrounding medium often made it difficult for that signal to escape cleanly. Which is why JADES-GS-Z13-1 startled astronomers. This galaxy is seen when the universe was only about 330 million years old, almost absurdly early. And yet it appears to show unexpectedly strong Lyman-alpha emission, stronger than many scientists thought likely at such a time. That does not merely suggest a bright galaxy. It suggests a changed environment. For Lyman-alpha to emerge clearly, the galaxy likely sat inside a region where the surrounding hydrogen had already been significantly ionized. In other words, it may have been enclosed within a bubble of relative transparency, a local clearing inside the cosmic fog. That is a remarkable image. The universe at this epoch was not supposed to be uniformly transparent. Ionization had begun, but large portions of intergalactic space should still have been neutral enough to suppress exactly this kind of signal. So if JADES-GS-Z13-1 really shows strong Lyman-alpha, then something around it had already transformed its neighborhood. What could do that? One possibility is a population of extremely hot, massive stars, perhaps unusually effective at pumping out ionizing radiation. Another possibility is that a growing black hole contributed to the ionization. A third possibility is that the galaxy existed in a dense region with nearby sources helping to carve out a large ionized bubble. Perhaps the galaxy was not alone in clearing the darkness. Whatever the exact explanation, the observation suggests that local transparency could emerge earlier than many models expected. That matters enormously. Ionization is one of the defining transitions in the history of the universe. It marks the shift from an opaque or semi-opaque intergalactic medium to one that allows light to travel more freely. Understanding when and how that happened requires knowing what the first powerful radiation sources were, how clustered they were, and how effectively they changed their surroundings. JADES-GS-Z13-1 may be a clue not just about one galaxy, but about the ecology of cosmic dawn. It tells us that some early sources were not merely shining, they were altering the medium around them fast enough to become visible through it. They were, in a sense, teaching the universe how to become transparent. This is where the story becomes almost eerie. We tend to imagine the early universe as distant in time, but also distant in legibility, as though the fog of primordial hydrogen should keep its first chapters mostly hidden. Yet, here is a galaxy whose light may be reaching us, because it already opened a window in that fog. It is not just visible. It may be visible because it had already begun clearing its own stage. In a strange way that gives the object agency, not literal agency, of course, but narrative agency. It is not passively sitting there waiting to be observed. It is actively part of the process that made observation possible. Its radiation may be one of the reasons its own signal can travel. Of course, caution remains essential. Spectral interpretation at these redshifts is hard. Extraordinary claims about early Lyman-alpha need scrutiny, follow-up, and the possibility of revision. Scientists must ask whether the signal is robust, how it fits into the broader dataset, and whether the line could be influenced by subtler effects. But once again, even the cautious version of the result is powerful. If local ionized bubbles existed this early, then the sources driving ionization may have been more intense, more clustered, or more efficient than expected. That does not break cosmology. It sharpens it. It tells us the young universe may have been less dim, less shy, and less uniform than our cleanest average picture suggested. And there's another important consequence: selection. If galaxies that open ionized bubbles become easier to detect, then the early objects we observe may be biased toward the overachievers. Webb may be showing us the first systems that succeeded in forcing visibility on a still reluctant cosmos. That would mean our earliest sample is not necessarily typical. It may already be pre-selected for power, which makes every discovery both more exciting and harder to interpret. Are we seeing the average young universe? Or are we seeing the first galaxies capable of announcing themselves across the fog? That question will matter again and again as more data arrive. And then there is the matter of order. Because even if a galaxy is bright, chemically advanced, and radiatively powerful, one expectation still seems especially hard to abandon. Surely the earliest galaxies should still be structurally chaotic. Yet one of the deep space discoveries now challenging astronomers suggests that even this expectation may have to soften. Chaos is cheap in the universe. Order is expensive. That is not a moral claim. It is a historical one. Order usually requires conditions to persist, disturbances to be survived, and structure to settle into something durable. We see this everywhere in cosmic history. Planetary systems emerge from disks. Galaxies build recognizable forms over long spans of time. Stable, elegant structures often look easy only because the violence that preceded them has been forgotten. That is why Rebels 25 is so provocative. Seen when the universe was only about 700 million years old, this galaxy appears to be strongly rotation-dominated. In other words, much of its motion seems organized into coherent spinning rather than random turbulence. It is not the Milky Way reborn in miniature. It is not a modern spiral galaxy transported backwards in time. But it does look more dynamically settled than many scientists expected for such an early epoch. And that matters because one of the broad assumptions about the first galaxies is that they should be messy. Gas flows should be turbulent. Mergers should be common. Structures should still be in assembly. The early universe was active, dense, and violent. Under such conditions, highly ordered rotational systems were thought to take longer to emerge. Yet Rebels 25 suggests that at least some galaxies reach that kind of coherence astonishingly early. Why is that hard to explain? Because a disk galaxy is not just a pile of matter. It is matter that has conserved angular momentum in a useful way. Gas has to fall in, cool, settle, and avoid being so violently disrupted that no stable large-scale rotation can dominate. Star formation and feedback must occur without completely scrambling the structure. The galaxy must somehow retain enough coherence to become dynamically cold relative to the more chaotic motion expected in young systems. This is not impossible in theory, but it is uncomfortable in timing. If Rebels 25 is what it appears to be, then some pathways to galactic order were shorter than many models emphasized. Perhaps gas accretion in certain halos was smoother than expected. Perhaps some environments were unusually favorable for disk formation. Perhaps internal processes regulated turbulence faster than simulations captured. Perhaps early halos with the right angular momentum history could produce order remarkably quickly. Whatever the mechanism, the discovery challenges a deeply intuitive idea about cosmic evolution, that refinement must come late. Maybe not. Maybe the universe can, under the right conditions, move from violent collapse to structured motion much faster than our narrative instincts prefer. Maybe disorder was common in the young cosmos, but not absolute. Maybe islands of composure appeared early, surrounded by chaos, just as ionized bubbles appeared early inside neutral fog. There is something elegant about that possibility. Cosmic dawn may not have been a uniform transition from crude beginnings to mature structure. It may have been patchy in every sense, patchy in transparency, patchy in chemistry, patchy in dynamical order. Some regions ran ahead, some systems accelerated, some galaxies became not merely luminous, but organized. That is what makes Rebels 25 more than a curiosity. It adds a third dimension to the emerging tension. Jades GSZ, 14.0 suggests chemical maturity. jades GSZ 13.1 suggests early local transparency. Rebels 25 suggests structural coherence. Together, they imply that the early universe may have advanced along several developmental axes at once, not just brighter, more mature, not just more mature, more visible, not just more visible, more ordered. At that point, the old picture begins to feel less like a slight underestimation and more like a narrative written in too calm a tone. There is also a danger here worth noticing. Human beings often over-romanticize order. When we see a rotating disk galaxy, we are tempted to treat it as a triumph over chaos, a sign that the universe has settled down. But rotation can also be the record of a very particular violent history. Gas infall, torques, mergers, and cooling all contribute to the final form. The elegance of a disk does not erase the turbulence that helped produce it. What Rebels 25 tells us is not that the early universe was peaceful. It tells us that peace, or something like it, may have emerged locally much sooner than expected. And yet, again, caution matters. A single galaxy does not dictate. When data challenge expectation, the healthy scientific response is not panic. It is branching. Researchers begin asking what combination of revised assumptions, overlooked processes, and new evidence can reconcile the old framework with the new observations. In the case of the early deep space anomalies, several serious possibilities have emerged, and each changes the story of cosmic dawn in a different way. One possibility is that early stars were different. This is perhaps the most compelling line of thought. The first stellar populations formed from low metallicity gas and that may have favored more massive stars than are common today. Massive stars emit enormous amounts of ultraviolet radiation, live short lives, and produce heavy elements quickly. If early galaxies were packed with such stars, they could appear brighter than expected for their stellar mass, enrich themselves faster, and ionize surrounding gas more effectively. This single idea has the attractive feature of addressing several tensions at once. Another possibility is that star formation efficiency was much higher in the early universe than many models assumed. In some halos, gas may have collapsed and turned into stars with startling effectiveness before feedback shut the process down. If so, galaxies could build up significant luminosity and even considerable mass in very short timescales. A third possibility involves active black holes. Accreting black holes can contribute substantial luminosity and ionizing power. They can make a galaxy look brighter than starlight alone would allow. They can help carve ionized bubbles in surrounding gas. They can complicate spectral interpretation and distort the usual relationship between brightness and stellar mass. If young galaxies hosted rapidly growing black holes, then some of the early surprises may reflect mixed populations of stars and central engines. But this explanation opens another puzzle. How did those black holes grow so fast? A fourth possibility is that the early universe was highly patchy in a way that matters observationally. Some regions may have been overdense and therefore advanced more quickly in structure formation. A galaxy inside such a region could form earlier, assemble faster, and live among neighboring sources that helped ionize its environment. If Webb is picking up these overachievers first, then our initial sample may exaggerate how typical they are. That would not erase the mystery. It would redefine it as a problem of rarity and selection rather than universal rule. A fifth possibility is that the models translating light into stellar mass, age, and composition are still too anchored in later universe assumptions. Nebular emission, binary stars, low metallicity stellar atmospheres, dust geometry, and unresolved source blending all affect interpretation. As those models improve, some apparently impossible galaxies may become merely uncomfortable rather than extreme. That distinction matters, but not as much as some headlines imply. A galaxy does not have to remain maximally shocking to still teach us something profound. And finally, there are the more adventurous possibilities. Some researchers have wondered whether the tensions point toward changes in dark matter behavior. alterations to small-scale structure formation, or other beyond-standard ingredients. These ideas are not impossible, but they occupy the far edge of the discussion for a reason. Before revising the foundations of cosmology, scientists want to exhaust the possibilities available within more ordinary astrophysics. History suggests that nature often surprises us through complexity before it surprises us through revolution. Still, it is worth noticing something important. No single explanation currently dissolves every tension with perfect elegance. A top-heavy stellar population helps with brightness, enrichment, and ionization, but says less directly about dynamical order. Black holes help with luminosity and local transparency, but demand early seeding and rapid growth. Selection effects explain why we may notice unusual systems first, but cannot make real anomalies disappear if they continue accumulating. Interpretive bias can shrink mass estimates, but cannot wish away repeated evidence of a universe moving fast. That is why the story remains so alive. The early deep space discoveries are not a mystery because scientists have no ideas. They are a mystery because scientists have several good ideas, none yet complete, and reality has not told us which combination it prefers. We should linger on that because it reveals the true shape of scientific frontier work. The public often imagines that science alternates between ignorance and final answers. In fact, it often lives in a more interesting middle state, where multiple partially successful explanations compete, overlap, and force one another to become more precise. The early universe is now in exactly that state. Researchers are not wandering in darkness. They are standing in an overlit room full of plausible doors, trying to figure out which ones actually lead somewhere. For now, the safest summary may be the most unsettling one. The young universe appears to have had multiple ways of overperforming. Chapter 12. What shouldn't exist really means in science. It is tempting to hear the phrase "arwa shouldno t exister for" and imagine a cosmic scandal, a law broken, a contradiction revealed, a universe caught doing something forbidden. But that is not how science uses the phrase when it is being careful. In practice, "shouldn't exist" usually means something like this. Under a widely used framework, with a particular set of assumptions, an object of this type, at this time, with these inferred properties, is far less likely, less common, or less easily produced than expected. That may sound less dramatic. It is also much more powerful. Because what science fears most is not impossibility. It is tension. Impossibility is often easy to dismiss as a mistake. Tension is harder. Tension means the data and the model are still in the same world together, but they are beginning to pull against each other. And tension, when it survives scrutiny, is often where progress begins. The deep space anomalies represent exactly this kind of tension. They do not tell us that gravity has failed. They do not tell us that the Big Bang never happened. They do not tell us that cosmology is dead. They tell us that the developmental story we told about the first few 100 million years may be incomplete, overly conservative, or too dependent on assumptions imported from later cosmic eras. That is a serious problem. But it is a scientific problem, not a theatrical one. This distinction matters because public discussions of frontier astronomy often veer toward extremes. One extreme says everything is broken. The other says everything is exaggerated. Both responses are lazy. The more interesting truth is that anomalies are usually neither total revolutions nor trivial misunderstandings. They are stress points. They show where a model is under strain. And models under strain are where science gets interesting. There's a long history of this. Planetary motions once revealed discrepancies that led to deeper gravitational understanding. Stellar spectra forced the discovery of physical conditions impossible to reproduce casually on Earth. Galaxy rotation curves pushed the dark matter problem into center stage. The acceleration of the universe opened the problem of dark energy. In each case, the anomaly did not arrive with an instruction manual. It arrived as persistence. That is the question facing the new early universe discoveries. Will they persist? If some of them fade under better analysis, that is normal. Frontier astronomy is difficult. If some remain and more like them appear, then the field will have no choice but to absorb the lesson. The early universe was more efficient, more diverse, more locally advanced, or more deceptive than earlier models implied. Either way, the phrase "shouldn't exist" has already done one useful thing. It has forced the public to notice that cosmology is not a static archive of settled facts. It is a live negotiation between theory and observation. The deepest parts of the sky are not just beautiful, they are argumentative. And perhaps that is the most honest thing one can say about science itself. Science is not a catalog of things we know forever. It is a method for surviving the moment when reality refuses to fit the sentence we wrote for it. There is another subtlety hidden inside that phrase. Shouldn't exist according to what? According to a specific simulation. According to a class of stellar population models, according to a baseline expectation about abundance. Science lives and dies by those qualifiers. A result that defies one simplified model may fit another more flexible one. A result that looks impossible under ordinary star formation assumptions may become merely unusual if early stars were more massive or if black holes contributed significant light. That does not weaken the anomaly, it refines it. It turns the headline into a map, and maps are what scientists need when the territory starts looking strange. There is a discipline to real astonishment. Scientists are perfectly capable of feeling shock, fascination, even intellectual dread. But the stronger the surprise, the more methodical the response has to become. This is why, despite the emotional power of the new deep space discoveries, most astronomers are resisting the temptation to say that physics has broken. That restraint is not timidity. It is wisdom earned from history. Astronomy has seen many first-wave sensations soften over time. Distances are revised, spectral features are reinterpreted, unresolved sources break apart into multiple objects, mass estimates come down, dust turns out to matter more than expected, even genuine discoveries often become less sensational in headline form while becoming more important in scientific form. That is not a failure of the process. That is the process. The early universe is especially dangerous ground for overstatement because the data are so faint, the objects so distant, and the interpretation so model-dependent. A very high redshift galaxy is not a jewel sitting clearly on black velvet. It is a fragile assembly of photons, usually sparse, often noisy, always dependent on careful calibration and comparison. The farther back we look, the more the line between discovery and interpretation narrows. This is why the field cares so much about spectroscopy. Photometric estimates can flag candidates, but spectra can confirm redshifts and reveal more secure physical information. The same is true of cross-observatory work. A Webb image may identify a source. ALMA may help probe its gas, dust, or emission features. Together they build a stronger case than either could alone, and yet even with stronger cases, caution remains because one object rarely decides a theory. What matters is population. Are these galaxies common? Are they rare but real? Are they the first members of a larger family or exceptional outliers amplified by selection effects? Do revised models of early stars and gas reduce the tension, or does the tension deepen as more confirmed objects arrive? These are the questions of a field doing science responsibly. There is also a strategic reason not to declare a cosmological crisis too early. If the tension can be resolved through better astrophysics, improved models of stellar populations, black hole activity, feedback, or interpretation, then prematurely invoking radical new physics would be intellectually wasteful. Extraordinary explanations should be invited only after ordinary explanations have genuinely struggled. But here is the key point. Care is not the same thing as dismissal. Scientists are not being cautious because the discoveries are unimportant. They are being cautious because the discoveries are important enough to deserve rigor. The more profound the possible implication, the more carefully evidence must be weighed. This is one of the things the public often misunderstands about science. Confidence and uncertainty are not opposites. In good science, they are partners. Researchers can be highly confident that something interesting is happening while remaining uncertain about exactly what it means. In fact, that combination is often the sign of a field at its healthiest. The early universe discoveries live in that zone. Few serious astronomers doubt that Webb and ALMA are revealing an unexpectedly rich and challenging picture of cosmic dawn. The debate is about magnitude, mechanism, and meaning. How severe is the tension? Which assumptions are failing? How much of the anomaly is due to interpretation? How much reflects real astrophysical acceleration? Those are not signs of confusion. They are signs that observation has finally become strong enough to force theory into conversation. And that is what every good telescope is ultimately for. Not to confirm what we already believed, but to discover whether belief was getting ahead of reality. It is also worth saying that caution protects wonder from self-destruction. If every difficult observation is immediately sold as the end of modern science, then careful correction later feels like anticlimax. But careful correction is not anticlimax. It is how wonder survives contact with truth. The public is not served by being promised a cosmological apocalypse every time a model needs revision. The public is served by being invited into the actual drama of science, which is slower, more exacting, and in many ways more beautiful than panic. The universe does not need us to exaggerate it. It is already strange enough. At the center of nearly every explanation for the deep space anomalies lies the same deeper question. What was the young universe really like when its first luminous engines switched on? Not in a broad textbook sense, in detail. How massive were the first stars? How quickly did they form? How efficiently did they enrich their surroundings? How soon did black holes appear? How quickly did those black holes grow? How clustered were the earliest sources of radiation? How patchy was reionization? How different was the physical texture of cosmic dawn from the average picture we have long carried in our heads? These questions are no longer abstract. They are now observationally urgent. If the first stars were unusually massive, then they would have burned bright, died young, and flooded the cosmos with ultraviolet radiation. They could help explain both rapid oxygen production and early ionized bubbles. If black holes formed early and fed aggressively, they could contribute extra luminosity, drive local ionization, and alter the observable properties of galaxies in ways that make them look unusually mature. In that sense, the early anomalies may not represent separate mysteries at all. They may be interconnected symptoms of a universe whose first luminous systems were more extreme than standard intuition allowed. There is something almost cinematic about that possibility. We are used to imagining youth as fragility, but perhaps cosmic youth was intensity. Perhaps the first stars were not hesitant candles, but blazing furnaces. Perhaps the first galaxies were not merely tentative assemblies, but highly compressed engines of transformation. Perhaps the first black holes were not late-coming complications, but active participants almost from the beginning. If so, then the early universe was not quiet and primitive in any ordinary sense. It was chemically simple, yes, but simplicity of ingredients may have enabled extremity of process. A hydrogen-helium cosmos under gravity does not need heavy complexity to become violent. It only needs collapse, density, and time, and perhaps less time than we imagined. This possibility reframes the whole mystery. Maybe the universe did not produce impossible galaxies. Maybe it produced galaxies in conditions more severe, more efficient, and more non-linear than our models had fully captured. That would mean Webb is not catching the cosmos breaking the rules. It is catching the cosmos using the rules more aggressively than we expected. There is an important conceptual shift here. Human beings often inherit a slow version of cosmic history. We imagine the universe beginning simple and then gradually, almost reluctantly, climbing toward complexity. But perhaps complexity in astronomy is sometimes front-loaded. Perhaps there are eras when conditions strongly favor runaway transformation, when youth is not hesitation, but leverage. The early universe may have been one of those eras, a time when low metallicity gas, rapid collapse, intense radiation, and compact structures produced extraordinary outcomes on compressed schedules. If that is true, then the first stars and the first black holes were not merely the opening cast, they were tempo makers. They set the speed at which matter could become more than matter, at which light could modify its environment, at which chemistry could cease being primordial and start becoming historical. And there is an unsettling consequence. If the earliest luminous systems were that intense, then what we call the first observable galaxies may already be second-generation outcomes in important ways. By the time we detect them, unseen prior stars may already have lived and died. Hidden black hole seeds may already have begun feeding. Their environments may already have been sculpted. The earliest visible universe may not be the earliest active universe. It may be the earliest stage at which activity became bright enough to catch. That means the young cosmos may have a kind of hidden prehistory just behind the observational curtain. And every surprising galaxy may be hinting at that unseen layer. There is a particular kind of excitement that takes hold whenever astronomy produces a difficult object. It begins with a phrase like, "This shouldn't exist," and almost immediately graduates to a more dramatic one. Physics is broken. The phrase spreads because it satisfies several appetites at once. It offers rebellion against authority. It turns technical uncertainty into existential spectacle. It flatters the audience with the feeling of witnessing a revolution. It transforms complicated science into a clean emotional event. And most of the time, it is wrong, or at least premature. Physics is not a single brittle statement waiting to snap. It is a layered structure of laws, approximations, effective theories, empirical constraints, and domain-specific models. When astronomers find tension in early galaxy formation, they are not usually confronting the failure of all physics. They are confronting the possibility that some assumptions about star formation, feedback, interpretation, black hole growth, or population statistics need revision. That is important. It is also very different from saying reality has demolished the foundations. The reason this distinction matters is not merely academic. It determines how science protects itself from intellectual self-sabotage. If every anomaly is treated as proof that everything is wrong, then actual conceptual revolutions become harder to recognize, because the word revolution has already been spent too cheaply. The young universe is an extraordinarily difficult regime to model. There are reasons to expect surprises there. The first generations of stars were unlike later ones. Ionization was patchy. Feedback was fierce. Gas physics was extreme. Observational inference is delicate. Under such conditions, it would be surprising if our first detailed observational look produced no tension at all. Tension is not an embarrassment. It is evidence that science has reached the frontier, and frontiers are supposed to feel unstable. That does not mean there can never be deeper implications. Sometimes repeated anomalies do point toward more profound changes in theory. But those changes emerge from persistence, from cross-confirmation, from the failure of simpler explanations, from evidence hardening over time. They do not emerge because a headline was written in a sufficiently apocalyptic font. In the present case, the responsible position is strong but measured. Something real is happening in our understanding of the early universe. The first galaxies appear more capable, more complex, or more observationally tricky than the earlier consensus allowed. The precise revision required is not yet known. That's enough to be scientifically thrilling. And perhaps there is an irony here worth noticing. People often assume science becomes less exciting when it becomes more careful. In truth, care is what allows excitement to survive contact with reality. Without discipline, wonder burns out into noise. With discipline, wonder becomes knowledge. The deep space anomalies deserve that kind of wonder, not because they have broken everything, but because they have broken complacency. Complacency may be the true thing that science is designed to destroy, not confidence, not rigor, not even provisional trust in a successful model. Complacency. The assumption that the broad outline is so secure that the details no longer matter. Webb has reminded cosmology that details matter enormously, especially near origins. A model can be right in spirit and wrong in tempo. It can be powerful in architecture and weak in local execution. The universe can endorse your laws and still embarrass your story. That is what is happening here. Not the collapse of reason, the collapse of overconfidence, and those are not the same event at all. Suppose, in the end, cosmology survives all of this without any foundational crisis. Suppose improved stellar models lower some mass estimates. Suppose some galaxies turn out to be less extreme than first reported. Suppose black holes, early star populations, and environmental patchiness explain much of the tension. Suppose the standard cosmological framework remains broadly intact. Would that mean the excitement was overblown? Not at all, because even in that outcome, something extraordinary has happened. The universe has revealed that its earliest luminous epoch was richer than we knew. The first galaxies were not mere vague placeholders on the road to later structure. They were active, chemically transformative, dynamically varied systems living inside a patchy environment of rapidly changing transparency. Cosmic Dawn, once a mostly theoretical chapter, has become a detailed observational landscape. That is a revolution in understanding, even if it is not a revolution in foundations. Think about what Webb and ALMA have already done. They have moved the young universe from speculation toward direct confrontation. They have shown us that the first few 100 million years were not beyond empirical reach. They have turned the earliest galaxies from inferred abstractions into objects with personalities, some overbright, some chemically expressive, some surprisingly visible, some startlingly orderly. This changes the emotional structure of cosmology. The early universe no longer feels like a blank preface, it feels inhabited. And that matters because humanity has always measured itself partly by origin stories. We want to know not only how the universe works now, but how it first learned to work at all. When did the first stars ignite? When did the first elements beyond hydrogen and helium appear? When did the darkness begin to break? How quickly did galaxies become places with internal histories? These are not decorative questions. They are questions about how complexity enters reality. Every heavy element in your body was made possible by ancient stars. Every planet, every ocean, every atmosphere, every chemistry-rich world depends on the universe first learning how to build beyond simplicity. The early galaxies are therefore not just exotic. They are ancestral. When one of them appears chemically advanced at 300 million years, that is not just a timeline issue. It is a clue about how early the pathways to later complexity were opened. When one of them seems to carve an ionized bubble in surrounding gas, that is not just a spectral issue. It is a clue about how the universe learned to become transparent. When one of them appears orderly in rotation, that is not just a morphological issue. It is a clue about how quickly gravity, gas cooling, angular momentum, and feedback can negotiate a truce. That is the deeper reason these observations matter, even if every single one of them eventually finds a sober, non-revolutionary explanation. They are teaching us about rate, about tempo, about the speed at which the universe can pass from possibility to structure. They are showing us that the first few 100 million years were not empty setup. They were an era of decisions. By the time many of the photons now reaching Webb first left their galaxies, the cosmos had already decided where some of its first stars would cluster, where ionized bubbles would widen, where heavy elements would begin circulating, and where the earliest systems would start looking less like accidents and more like places. That is a profound shift in perspective. For a long time, the first galaxies lived mostly in the future tense of scientific imagination. We said they must have been small, must have been chemically poor, must have been highly irregular, must have struggled through a mostly neutral universe. Some of that remains true. But now the young cosmos is entering the past tense of observation. We no longer have only expectations. We have examples. Examples are dangerous things. Averages can be defended. Simulations can be tuned. General stories can be softened at the edges. But a real galaxy at a real redshift, with real spectral features and real internal motion, has a way of hardening philosophical questions into physical ones. It asks not what we prefer the universe to have done, but what the universe demonstrably managed to do. And once that question becomes empirical, cosmology is forced into one of its healthiest states: humility. Not the humility of surrender, but the humility of revision. The humility to say that our models may have been elegant without being complete. The humility to say that the early universe may have contained pathways to rapid complexity that we underweighted. The humility to admit that what looked like impossibility from a distance may turn out to be ordinary physics operating with extraordinary efficiency. And there is real beauty in that possibility. Because it means the universe may not need to break its rules to surprise us. It may only need to reveal how much power was hidden inside the rules all along. Once a scientific anomaly survives the first burst of excitement, the real work begins. Not the work of writing headlines, but the work of explanation. In the case of these deep space discoveries, several broad classes of explanation are now competing, overlapping, and sometimes combining with one another. None is fully satisfying on its own. None has won. But together, they define the frontier of what scientists are now seriously considering. The first possibility is that early star formation was more efficient than many models assumed. This may sound technical, but it is actually one of the most intuitive ideas on the table. Galaxies form inside dark matter halos. Gas falls into those halos. Only a fraction of that gas becomes stars. If early galaxies were simply better at turning gas into stars than expected, then several puzzles become less severe. Brighter galaxies become easier to explain. More massive stellar populations become easier to explain. Faster chemical enrichment becomes easier to explain. But efficiency is not a magic word. It has to come from somewhere. Gas must cool rapidly enough to collapse. Feedback from stars and supernovae must not choke off subsequent star formation too aggressively. The geometry of inflows may matter. Halo mass may matter. Environment may matter. Even the turbulence of the gas can influence how readily star-forming regions condense. So to say that early star formation was more efficient is really to open a family of questions about the conditions under which the first galaxies converted raw material into light. A second possibility is that the stellar populations themselves were unusual. The first generations of stars formed in a universe with very few heavy elements. That changes how gas cools, fragments, and collapses. It may also change the distribution of stellar masses. If early star formation favored more massive stars than is common in the modern universe, then those galaxies would appear brighter for a given amount of stellar mass. They would also enrich themselves more quickly, because massive stars live fast and die young. A top-heavy stellar population, as astronomers often say, could therefore help explain both the luminosity puzzle and the oxygen puzzle at once. This is one reason the early universe remains such a difficult place to interpret. Light does not tell you mass directly. It tells you radiation. To translate radiation into stellar mass, you must assume something about the stars producing it. If those stars differ systematically from modern expectations, then some apparently overmassive galaxies may not be as overmassive as they first seem. They may instead be overluminous relative to the templates we were using. That sounds like a retreat from the anomaly, but it is not necessarily a retreat. If the early universe really did produce systematically different stellar populations, that would itself be a major discovery. It would mean that the first galaxies cannot be understood simply by projecting local astrophysics backward in time. It would mean cosmic dawn had its own rules of expression, even if those rules remain compatible with basic physics. A third explanation centers on black holes. Growing black holes can contribute intense radiation to a galaxy's output. If some early galaxies hosted active galactic nuclei, then a portion of the brightness attributed purely to stars might instead come from accreting black holes. That could distort infrared masses and also help explain strong ionizing emission. In the case of JADES-GS-Z13-1, for example, an early active nucleus has been discussed as one possible source of the energy required to help carve out an ionized bubble. Black holes are especially seductive as explanations because they combine brightness, violence, and early growth into one package. But they also raise their own timing problem. To matter this early, they must themselves have formed and grown quickly. So appealing to black holes does not remove the tension. It often relocates it. Instead of asking how galaxies became bright so early, we ask how their central black holes became powerful so early. A fourth possibility is that the early universe was more patchy than our broad brush averages made it seem. This matters for both detection and interpretation. Cosmic dawn was not a uniform curtain rising across the entire sky at once. Different regions of the universe were evolving at slightly different rates depending on local density, merger history, gas supply, and the clustering of early sources. Some regions may have started forming stars sooner. Some may have produced overlapping ionized bubbles earlier. Some halos may have experienced unusually favorable accretion. If so, then Webb may be sampling not a clean average of the early universe, but a mix of ordinary young galaxies and exceptional overachievers living in locally accelerated neighborhoods. This kind of patchiness could help explain why certain objects look more mature than the global timeline seems to allow. They are not breaking the epoch, they are outrunning it locally. But here too, caution is required. Patchiness can reduce tension, but only to a point. If too many objects look too advanced, then local exceptionalism stops being an explanation and becomes a symptom of a broader underestimation. A fifth possibility is more observational and methodological. Maybe some of the inferred properties are still wrong. This is not skepticism for its own sake. It is part of the scientific process. Frontier astronomy is hard. Photometric redshifts can be revised by spectroscopy. Emission lines can distort broadband colors. Dust can mimic age. Source blending can inflate brightness. Assumptions about star formation history can alter inferred masses. The safest position in early universe astronomy has always been that the first description of an extreme object is rarely the last. And indeed, some early Webb claims have softened with further work. Certain galaxies that initially looked impossible became merely challenging. Mass estimates shifted downward. Distances were refined. Interpretations became more cautious. That matters. But it does not end the story, because what remains, even after caution, is still remarkable. Enough galaxies continue to look brighter, more massive, or more mature than many pre-Webb expectations that the field is still working through the consequences. If all the tension had dissolved, the conversation would have quieted. It has not. It has become more disciplined, which is different. There is also a sixth possibility, and it is perhaps the most interesting of all. Maybe no single explanation is sufficient. Maybe the early universe was not doing one unexpected thing, but several compatible things at once. Perhaps the first galaxies formed stars with somewhat higher efficiency. Perhaps their stellar populations were somewhat more top-heavy. Perhaps some hosted active black holes. Perhaps reionization was highly patchy. Perhaps our templates were slightly off. Perhaps our selection effects favor the brightest and most evolved objects. None of those alone needs to rewrite cosmology. Together, they could significantly alter the expected appearance of cosmic dawn. This kind of multi-cause explanation is often how science actually progresses. Reality rarely arranges itself around a single dramatic answer. It offers overlapping influences, partial corrections, and layers of causation. The temptation to seek one decisive fix is human. The universe is often less theatrical and more intricate than that. Still, it is worth asking whether the anomaly might run deeper. Because if the early universe really was much more efficient at building luminous, enriched, and occasionally ordered systems than the models anticipated, then the issue is not merely one parameter needing adjustment. The issue is that our intuition about how quickly complexity can emerge under primordial conditions may itself need revision. And that is where explanation becomes philosophy. What exactly did we assume about beginnings? Did we assume that youth must look crude? Did we assume that structure must take its time? Did we assume that simplicity of ingredients must enforce simplicity of outcomes? The more Webb and Alma continue to test those assumptions, the more the puzzle stops being a narrow astrophysical problem and becomes a broader lesson in how easily human expectation mistakes gradualism for necessity. There is a particular kind of sentence that flourishes whenever astronomy produces a surprise. Everything we know is wrong. It is a sentence engineered for emotional impact. It satisfies a certain appetite in the public imagination. It makes discovery feel explosive, immediate, revolutionary. And sometimes science really does experience moments when an old framework collapses under the weight of data. But most of the time, the truth is more interesting than collapse. The truth is that nature pushes on the joints of a theory long before it shatters it. Measurements accumulate, tensions persist, assumptions are revised, a model survives in broad outline while changing in detail. Or a new layer of physics emerges not by replacing everything beneath it, but by correcting where the old model was being used beyond its comfort zone. That is why the phrase, "always these galaxies should not TMTT exist," needs handling with care. It does not mean the universe has violated itself. It means the galaxies do not fit comfortably inside a set of expectations drawn from current models. That may sound less dramatic, but it is actually more powerful, because it tells us where science lives, not in the false choice between certainty and disaster, but in the tension between prediction and observation. If one day cosmology does undergo a major revision because of these early galaxy findings, it will not happen through a theatrical announcement that all previous physics was nonsense. It will happen through a sequence of narrower realizations. Maybe star formation at low metallicity behaves differently than assumed. Maybe certain feedback processes were overstated. Maybe dark matter halo growth couples to baryonic physics in a subtly different way at the earliest times. Maybe ionization proceeds more unevenly than simpler models captured. Maybe black hole seeds formed through channels not yet fully appreciated. Each of those would be significant. None would require us to throw away all of modern cosmology. In fact, one of the strengths of science is precisely that it can absorb surprise without surrendering rigor. A theory that meets a challenge is not automatically dead. Sometimes it is being invited to mature. This is an important cultural lesson because cosmology is especially vulnerable to overstatement. Its subject matter is vast, ancient, and emotionally loaded. People want the story of the universe to come with cliff edges, forbidden secrets, and shattered paradigms. And sometimes the language of outreach encourages that appetite because wonder is easier to market when it sounds apocalyptic. But science owes itself something higher than excitement. It owes itself precision. And precision here means being able to say two things at once. First, these discoveries are genuinely extraordinary. They matter. They are not trivial. They are forcing astronomers to revisit some of the deepest assumptions about the pace of early structure formation. Second, extraordinary does not automatically mean catastrophic for the entire edifice of physics. Nature can be more efficient than our models without becoming irrational. The universe can surprise us without becoming lawless. This distinction matters because it protects the real wonder from the cheap version of wonder. The cheap version says, "Oh, physics is broken." The real version says, "Oh, physics may still be right in broad form, but richer, stranger, and more capable than our current implementations have managed to express." That second statement is harder, subtler, and in many ways more awe-inspiring. It suggests that the equations we already trust may contain consequences we have not yet fully learned to read. There is a long history of this in science. Newtonian gravity worked brilliantly for centuries, until certain regimes exposed its limits. Classical physics explained a huge amount of the world, until the quantum and relativistic realms made clear that deeper layers were needed. Yet even in those transitions, science did not advance by declaring every previous success meaningless. It advanced by identifying where older descriptions stopped being complete. Early galaxy cosmology may be moving through a similar, though perhaps less radical phase of clarification. Webb and ALMA are not necessarily announcing the death of the standard model of cosmology. They may be revealing that one of its most difficult chapters, the formation of the first luminous structures, was being told in a voice too smooth for the evidence now arriving. That is not failure. That is growth. There is also a practical reason scientists resist hyperbole. Hyperbole can obscure the actual scientific opportunities. If every anomaly is treated as total crisis, then the careful work of discrimination becomes harder. Which measurements matter most? Which predictions differ between models? Which observations would actually distinguish a top-heavy stellar population from an active black hole, or patchy reionization from an overestimated stellar mass? To answer those questions, researchers need a disciplined map of the problem, not a bonfire of old ideas. And those discriminating observations are coming. More spectra, more confirmed redshifts, better constraints on emission lines, more sensitive observations of dust and gas, higher resolution studies of kinematics, larger samples of very early galaxies. In other words, the next phase of this story will not be decided by rhetoric. It will be decided by accumulation. That may feel less cinematic than the phrase, "Oh, way, physics is broken." But in truth, it is more suspenseful, because accumulation is how reality slowly closes in on error. If these galaxies only looked impossible because early interpretations were too hasty, the data will reveal that. If the tension survives, the data will reveal that too. And if the answer turns out to be somewhere in between, as it so often does, then the result will still be a deep revision of how we picture the universe at dawn. The most mature response to these discoveries is therefore not panic and not dismissal. It is watchfulness, a willingness to let the evidence become dense enough that theory can no longer answer with elegance alone. In that sense, the current moment in cosmology is less like a revolution already completed and more like a courtroom just beginning to hear the strongest witnesses. The headlines have made the accusation. Now, the data must testify. There is a reason these discoveries resonate beyond astrophysics. They touch something older than science. Human beings have always wanted beginnings to make sense. Creation stories, whether mythic or scientific, serve partly the same emotional function. They tell us how complexity arose. They explain how order emerged from what came before. They give shape to the transition between almost nothing we recognize and everything we now inhabit. That is why the first galaxies matter so much in the imagination. They occupy a sacred threshold, not sacred in a religious sense necessarily, but sacred in the sense that thresholds always are. They mark the passage from one condition of reality to another. Before them, darkness, neutrality, primordial simplicity. After them, light, chemistry, visibility, structure, inheritance. To discover that some of these threshold objects already look unexpectedly mature is therefore to experience a subtle philosophical disturbance. It suggests that beginnings may not always be tentative. It suggests that the universe may have crossed some of its greatest thresholds with startling decisiveness. We tend to imagine growth as gradual because that is how much of human life feels from the inside. Childhood becomes adulthood through accumulation. Civilizations rise over centuries. Knowledge compounds through generations. Even trees, mountains, and coastlines seem to mature slowly enough to reassure our sense of order. But the cosmos is not obligated to respect the tempo that makes human intuition comfortable. Under the right conditions, a young universe can move with breathtaking speed. Gravity does not hesitate. Massive stars do not hesitate. Radiation does not negotiate. Once enough matter gathers in the right way, transformation can become explosive. Light can appear where there was darkness. Elements can be forged where there was only simplicity. Motion can organize where there was turbulence. Entire environments can change character in spans that are brief on cosmic terms. That is part of what Webb has revealed. The deep universe is not merely ancient, it is consequential. Those photons from JADES-GS-Z 14-0 are not only old, they are witnesses to rapid enrichment. Those photons from JADES-GS-Z13-1 are not only distant, they are witnesses to early local transparency. Those measurements of Rebels 25 are not only records of remote motion, they are witnesses to order arriving before we thought it would. This gives the young universe a different emotional texture. It no longer feels like a simple nursery. It feels like a place where the first great acts had already begun. There is also something humbling here about the nature of expectation itself. We often mistake our theories for the universe's biography. But theories are not biographies. They are disciplined guesses about what reality has likely done under given constraints. They are powerful and indispensable, but they remain acts of interpretation. When Webb shows us a galaxy that seems to have compressed too much history into too little time, it is not humiliating theory for being theory. It is reminding us that nature is always prior to our description of it. That reminder has moral significance for science, not morality in the ordinary social sense, but in the sense of intellectual character. Good science requires the ability to love explanation without worshiping it, to build models confidently and abandon them gracefully when evidence demands, to feel wonder not only when a theory succeeds, but when reality exceeds the imagination that produced the theory in the first place. This is why the phrase "au shouldna" t exist is best understood not as a declaration of impossibility, but as an expression of model shock. The object exists. That part is settled or is on its way to being settled. The real question is what hidden assumptions made us think it would be less likely. Was it the assumed efficiency of star formation, the assumed shape of the stellar initial mass function, the assumed pace of chemical enrichment, the assumed topology of reionization, the assumed timescale for disks to emerge, the assumed rarity of certain environments? In every case, the discovery points beyond itself toward the architecture of expectation. This is what makes astronomy so philosophically rich. The sky is never just a collection of objects, it is also a mirror for the forms of reasoning we bring to it. A surprising galaxy does not only tell us something about galaxies, it tells us something about how we imagine causation, sequence, growth, and the possible. Perhaps that is why deep space anomalies can feel so intimate despite their distance. They remind us that human understanding is always provisional, always lit by partial light, always subject to correction by realities older than our species and farther than our language was built to hold. And yet we go on looking. That, too, matters. We are a local species on a minor planet, made of heavy elements forged in ancient stars, using machines of gold-coated mirrors and cryogenic detectors to read photons that began traveling billions of years before our world existed. We are using those photons to ask how complexity first entered the universe strongly enough to persist. There is something almost unreasonable about that ambition, and something deeply beautiful. Because in studying the first galaxies, we are not merely studying what is out there. We are studying the earliest ancestors of every later structure that made our own existence possible. In the beginning were not human stories, not civilizations, not biology, not planets. In the beginning were gravity, gas, radiation, and time. If the first galaxies learned to become substantial with shocking speed, then the roots of everything familiar reach into a universe that was already more determined, more creative, and more physically expressive than we had imagined. That possibility should not frighten science, it should enlarge it. So what in the end have scientists found in deep space that shouldn't exist? They have not found a literal impossibility. They have not found an object that violates mathematics. They have not found proof that the universe has abandoned causality, symmetry, or physical law. What they have found is something in its own way more unsettling. They have found that the early universe may have been astonishingly good at becoming itself. Astonishingly good at gathering gas into luminous structures, astonishingly good at igniting stars, astonishingly good at making heavy elements early. Astonishingly good at carving local windows through a still-fogged cosmos. Astonishingly good, at least in some cases, at building ordered motion out of primordial violence. JADES-GS-Z14-0 tells us that chemistry may have advanced faster than many models predicted. Oxygen appears there as a sign that stellar generations had already begun living, dying, and transforming their surroundings when the universe was still only a few 100 million years old. JADES-GS-Z13-1 tells us that transparency may have arrived locally earlier than expected. Strong Lyman-alpha emission at such an epoch hints that some galaxies or their environments were already opening ionized bubbles in a universe still thought to be largely veiled by neutral hydrogen. Rebels 25 tells us that order may not have waited politely for deep cosmic age. Coherent rotation, so early in the universe, suggests that under the right conditions, structure could settle more rapidly than our standard narrative preferred. None of these discoveries alone forces a grand overthrow. Together, they do something subtler and more important. They force attention. They force theorists to sharpen assumptions. They force observers to gather better spectra, larger samples, and deeper surveys. They force the idea of cosmic dawn to become less schematic and more empirical. And in doing so, they restore one of the healthiest feelings in science: unfinishedness. There is a temptation, when talking about the universe, to imagine that the deepest outlines are already known. Expansion, dark matter, cosmic microwave background, structure formation. The large framework is indeed powerful, but a framework is not a completed map. Inside that framework live chapters of enormous subtlety, and the first galaxies are one of those chapters. They are where dark matter halos, gas physics, stellar birth, stellar death, radiation, chemistry, black hole growth, and reionization all collide in the same young spaces. We are only now beginning to watch that collision directly. That is why this story feels alive. Not because science has failed, but because science has reached a region where the universe is still richer than our summary of it. And that richness matters beyond professional astronomy. It matters to anyone who wants to know how the world became capable of worlds, how the cosmos became capable of chemistry, how light first began to conquer the dark, not abstractly, but in actual places with actual histories. It may turn out that the standard cosmological picture survives with adjustments. It may turn out that some of the most alarming early interpretations were artifacts of limited data. It may turn out that unusual stellar populations, active black holes, and strong environmental patchiness together explain much of the tension without demanding any radical new physics. If that happens, the discoveries will still have changed our understanding, because they will have shown that the first galaxies were more varied, more dynamic, and more locally consequential than the older picture conveyed. And if the tension deepens, if more galaxies continue to appear brighter, more enriched, more visible, and more organized than expected, then the lesson will be even larger. It will mean that the early universe was not merely a simpler prelude waiting to mature. It was already racing toward light, racing toward chemistry, racing toward structure, racing toward the layered complexity from which every later star system, every rocky planet, every ocean, every atmosphere, and every living observer would eventually descend. There is something almost overwhelming in that thought. When we look into deep space, we are not just looking far away. We are looking at the speed of origin. We are watching a universe that, even in youth, may have wasted very little time becoming fertile, radiant, and strange. The first galaxies are not only relics, they are revelations. They tell us that the darkness after the Big Bang was not a static waiting room. It was a pressure-filled interval before ignition. And once ignition came, it may have spread with a force and efficiency we are only beginning to understand. So yes, scientists have found something in deep space that shouldn't exist. If by that we mean something our expectations had not made enough room for. Something that arrived too mature for the old timetable. Something that asks whether our models of the first few 100 million years were too cautious, too averaged, too gentle. Something that reminds us the universe does not owe us simplicity at the beginning, merely because simplicity comforts the mind. The cosmos may have begun in heat and abstraction, but by the time its earliest observable galaxies lit up the dark, it may already have been moving toward complexity with a speed that should leave us, even now, slightly breathless. And perhaps that is the most honest ending available. Not that the universe is broken, not that our theories are worthless, but that ancient light, arriving after more than 13 billion years of travel, is still capable of finding the weak points in certainty, still capable of teaching us that beginnings can be fiercer than expected, still capable of showing us that reality, when young, may already have been far more accomplished than we had imagined.